In previous videos, we've already looked at how real numbers can be represented in binary using a floating point representation. In this video, we're going to discuss the three major problems with using floating point representations in software. The first of these is that there are precision bits, which is the bits that come to the right of your radix point, and the number of them determines the precision of your floating point representation. But precision is often misconstrued as accuracy, and the two are not the same. Just because we have bits to the right of our radix point in the significand doesn't mean that we have many bits to the right of the radix point after the exponent is applied. So in some situations, we will find ourselves with bit patterns that represent incredibly tiny numbers that are fairly accurate, and the precision is sort of close to the accuracy in a sense. But in other circumstances, we will find ourselves with large exponents or just larger than other exponents we used, and we'll end up after their application with some value that is no longer as accurate as we might have hoped. And to exemplify this, I want to go with a real simple example. So we're going to take somebody, say their name is Amos. And Amos wants to buy some stuff. He wants to buy coal, and he wants to buy 3.47 kilos of coal, right? He wants to buy 3.47 kilograms of coal, and he wants to do this at the going market rate because it's so low, at $3.50 per kilogram, right? Now, when it comes time to pay, of course, I only have hundreds. So we got to deal with getting my change back. So he's going to pay with a $100 bill. Now the question is, what is the change? All right, how much do I get back? So we ought to be able to figure this out, and we could easily write a program that does it, and I've done that ahead of time so that you don't have to watch it. But we need to know what to expect. So let's take 3.47 and multiply it by, well, 3.5 really, and see what we get. So if we take 7 times 5, we should get 35. So that's a 5, carry the 3. 5 times 4 is 20, plus 3 is 23. 5 times 3 is 15, plus 2 is 17. All right, let me get rid of these guys, and then we'll go on to the 3. 3 times 7 is 21, so that's a 1, carry the 2. 3 times 4 is 12, plus 2 is 14, so that's a 4, carry the 1. 3 times 3 is 9, plus 1 is 10. So add the partial products, we get 5, 4, 1, carry the 1. 2 and 1, and then we had 1, 2, 3 total decimal places here, so we need 3 total decimal places in our answer, and that means we ought to receive, or we ought to be charged $12 and 145 thousandths for the actual 3.47 kilograms of coal at that price. So if we take $100, which is what I pay with, and then subtract from that $12.145, well, what should we get? It should be 87.855. And so that's what we want to see. We want to see that the total cost is 12.145, and when I pay with $100, we want to see that my change is 87.855. So what I've got here is a pre-written program. It's very simple. I only include one thing. It's standard I/O just for printing and scanning numeric values, all of which I will use as floats, just so we can get an idea of the consequence of using the floats. So we're going to read in a weight after the user has been prompted here. So how much weight of something, what's the price per weight. Once we have that, you can see here on this little bit, we're going to print out what the total is. So that's where we should see the 12.145 from the example we worked out by hand. Then it'll prompt us for how much cash we're going to pay with, and it will print out our change as the cash amount provided minus the total. Very simple. So let's compile this thing. Let's see here. May not see, I called it. And then we'll give it a run. How much weight? Why, 3.47 pounds of coal, please. How much is the price per weight? Why, it's the market price of $3.50. I guess we don't need the zero, but whatever. How much cash do we have? First, it said our total is 12.145, and then has lots of zeros after it. That's A-okay with me, because that's exactly what we worked out on paper. So how much cash? We got $100. What's my change? $87.854996. So it's definitely not dead on accurate, and this isn't arithmetic that involve complicated values. They're not even really big values. They're also not even really tiny values, right? They're not super close to zero. They're not super far away from zero. It's not negative. It's just very simple values. And yet we don't have precisely the right answer. So again, don't confuse precision with accuracy. And don't use floats for calculations that involve money, because it probably will not work out very well for you, because the floats are not really that accurate. We're going to see why in a little bit. But I want to make sure that we see that this isn't just some issue, say, with C. So I'm going to open up a Python 3 interpreter here. It's ready to go. And in Python, of course, you can just type mathematical expressions and it will calculate the results and print them out. So we're going to do the same thing. We'll start with the fact that I wanted 3.47 pounds of something at the cost of $3.50. And you'll see already here in Python 3, we don't have an accurate result. Where we would have expected 12.145, instead we got 12.145, and let me put some keyboard to work here. Looks like 11 zeros and then a 1. So it's very close, very, very close to the right answer, but it isn't the right answer. And we should take heed and notice that this is going to be the case. Now, if we were to do more calculations, the error would compound, right? And would potentially get new errors from other sub-calculations introduced. So please, be careful when you're using floats or doubles. You know, we could switch this to a double and maybe the error we see now will disappear, but that doesn't mean it doesn't have errors. It just means it doesn't have a visible error for this particular value. Right? Now, there is a second problem with using floating point numbers, and that is that accuracy, not precision, but accuracy, gets exponentially worse the further away from zero we get. So let's take an 8-bit representation for floating point. I've used the same representation over and over in previous videos, so we're going to mix it up today. Here's a sign bit. I realize that's the same. Now I'll give more bits to exponent than the significand, and I'll put the exponent first, more like the IEEE standard. And we'll give it 4 bits, and then we'll use the last 3 bits for the significand. Now we have to pick how the exponent and the significand work. So we're going to say that these are denormalized, and the reason I'm choosing that denormalized, the reason I'm choosing the significand to be denormalized is so that I know I'm working exactly with this bit pattern here. And it's 3 bits. Say B, and C. And if it's denormalized, that means the radix point will go here. Now to make the diagram I want to give for you easier to produce and understand and talk about, I don't actually want to deal with real valued numbers. So I'm going to make sure that our exponent forces all of these denormalized significands to turn out to be integers in the end. So whatever bit pattern we get, we're going to end up with a whole numbered value, which means I want to take and move this bit the radix point 1, 2 bits to the right. And so I'm going to say this is denormalized with a bias that's equal to +2. And that makes sure that every bit pattern we provide is an integer. All right, so let's draw some number lines here. And we're going to do that over a series of exponents. So the exponents, being biased, will be treated initially as, say, all zeros, then 0, 0, 1, then 0, 1, 0, and so on. But when it's all zeros, we're going to add 2 to it, which is going to move this radix point 1, 2 over. So the exponent bits will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and I doubt we will need to go further than this to see what's going on. So we'll leave the other half to our imagination. And for each of these, we're going to provide a number line that starts at 0. So we'll just draw a line over, another line over, another line over, and the fourth line over. Something like this. And we'll say that this point here is 0. And this, of course, is the positive direction on the number line. And there is, of course, negative numbers on our number line, and we can get negative numbers by just changing the sign bit from a 0 to a 1. And so the range is really a mirror image when we're dealing with floating point values. So we'll get the idea that whatever we draw here looks the same way in the other direction, and so we'll have a better concept of what's going on. So when our exponent bits are 0, 0, 0, that is the number 0 plus 2 will give us an exponent of +2, so this moves all the way over. And we have then 3, this should have been 4 bits big, holy moly, no big deal, 0, 0, 0, 0. So we only looked at a quarter of the 16 exponents, but that's fine. When the exponent bits are all zeros, we're going to get a true exponent of +2. That's going to move this radix point over to here. And then what we're going to have are just integers. And so if the significant is all zeros, then this will give us the integer value of 0, which is this point. If the 3 bits for the significant are 0, 0, 1, then we're going to get a value of 1, which will be here. Now, there are 3 bits for the significant, so we get 8 different values, including 0, so it's 0 to 7. That's 0, 1, 2, 3, 4, 5, 6, and 7. All right, so that's all the numbers that we can represent here in blue with the exponent bit pattern 0, 0, 0, 0. Then we're going to move the exponent up to the value 1, which will make the true exponent after we add 2 plus 3. So this will become 1, 2, 3 over to the right. So it's going to be a 0 padded on here. So if the significant bits are all 3 of them zeros, we're going to get 4 zeros before the radix point. So that's this value right here. If we then add 1, so it's 0, 0, 1, because the radix point is going to move 1 further, it's really going to be 0, 0, 1, 0, which is the number 2. So we can represent this guy here. If we make this a 2, 0, 1, 0, then when we bump that up by 1 extra digit, it's going to become a 4. So that's over here. And we're going to get 8 different values starting at 0, each of which are 2 integers apart. So we'll go 1, 2, 3, 4, 5, 6, 7, and 8. All right, and this is the number 0, 2, 4, 6, 8, 10, 12, 14. But please notice that 0, 2, 4, and 6, each of those values are ones that we can already represent using a different exponent. So we didn't actually gain any new values with that particular representation. We can just show that value with a different exponent, which will help us with performing arithmetic operations. Now we'll go to 2, and the same thing is going to happen. Effectively, that's going to move the radix point 2 positions past this, scaling all of our original 8 represented values by 4, so multiplying by 4. So that means it's going to go twice as far as the previous exponent. So we've got 1, 2, 3, 4, 5, 6, etc. Then when we go up again, we'll get another one that goes twice as far as the previous. So 1, 2, 3, 4, etc. Right. So what does this mean? Well, it means that an awful lot of the numbers that we can represent, especially with higher exponents, half of them at any given exponent above the exponent bits of 0, half of those are guaranteed to be numbers that we've already represented using some other exponent. And that means out of our total representational capacity, say with our example here, 8 bits. 8 bits gives us 256 different bit patterns. But some percentage of those bit patterns are not unique abstract values to the human. In fact, if we think about it, think about 0, right? In our diagram here, we have 4 different zeros, and those are the positive zeros. We can make them negative as well, and so there's 4 negative zeros. So effectively, with mirroring, we've already shown 8 different zeros. Well, how many zeros are there? Well, there's a positive and a negative one for each of our different possible exponents, because we can just have the significands be all zeros, right? So how many bits are involved? Well, if we've got the significant bits all set to 0, then there's 4 other bits left. There's the sign bit, and then we have the 3, so that we get 4 altogether. There's 3 bits for the significant. So then we'll have the sign bit, and then 4 bits more for the different exponents that we could have that take 0 nowhere away from itself. So 5 bits don't matter at all as long as the low end 3 bits are all zeros. And that means that there are 32, 2 to the 5th, 32 different representations of the number 0, right? And that's 32 out of 256 different values that we have. 32 out of 256 different values, right? That's 1/8. 1/8 of our entire representation in this particular model is the number 0, right? But yet we can still represent some numbers that are very large. But the distance between those numbers, the next number we can represent, gets further and further and further and further away the further away we get from 0, right? And so that's a fundamental issue that we have. All right, now the last big problem that we have with floating point representations, the third problem, is that the significant is typically normalized. And the reason we do this is because we want to make sure that we get as many bits of precision as possible in hopes of having more accurate values, right? But precision is not accuracy. So we assume there is a 1 followed by the radix point, and then the encoded significant bits are just placed after this, right? So if we have, as in our example that we just did, 3 significant bits, but we encode them in a normalized fashion rather than denormalized, then we're going to have a 1, a radix point, and then the 3 bits. So we still end up with 8 different significants that we can have because there are 3 bits that vary, but they all already had a 1 in them, which means we get 4 total bits of representation, even though we only stored 3. The trouble, though, is because we have a 1 when we do a normalized representation, because there's always that 1 then the radix point, we can't intuitively represent the value 0, which may not seem like a big thing, but it means that some software or hardware implementation must be made that looks out for a specific bit pattern to flag as the value 0, or as one of the values 0, depending on whether we want multiple values of 0. So in recap, there are 3 problems with using floating point. The first is that precision is not the same as accuracy. We really have to be aware of that anytime we use a floating point value, whether it's a float or a double, or even if we go to quad type precision representations or octuple representations, which most people do not do. But no matter what, the precision is not going to necessarily give us accuracy, right, because of the issues that we've seen. The second problem, which is directly related to this, is that the accuracy gets worse and worse the further away from 0 you go, whether it's positive or negative. And then the third big problem was that with normalized representations of significance, which is most of what we do, you can't intuitively represent in 0, and so there is fancier stuff behind the scenes, more complicated processing that has to take place to deal with it. If you got any questions, please leave a comment below or contact me through the class website.